Let's now take a look at an example. So we're going to consider a parallel plate capacitor which has a separation of 2 millimeters and a voltage of 1 kilovolt applied across it. We're told that the dielectric between the two metal plates is polystyrene, which has a relative permittivity of 2.55. We want to find the electric field, the polarization, and the bound surface charge density rho sub ps. And so we're also given this configuration where we see that our electric field is in the x direction. So we see it's going from x equals 0 on the left plate to x equals 2 millimeters on the right plate. And we see we have our polystyrene material in between our two metal plates there as well. Okay, so in this case, if we're finding E, it's relatively simple because we don't have any spatial or time dependence of our voltage. If we did, we could go back to the equations from the previous unit, but in this case, we can just say that the magnitude of that electric field is just going to be the voltage divided by the distance between the two plates. So we have our 1 kilovolt, which is 1,000 volts, divided by our separation, which is, we want to put it in meters, so 2 times 10 to the minus third meters, and we get 5 times 10 to the fifth volts per meter. And based on our given orientation then, so using this information here with our x equals 0 to x equals 2 and our potential being in the polarity as shown with the positive at x equals 0, we can then change this magnitude to a vector, and we can say that our E is going to be equal to, and let's go ahead and change it to 500 kilovolts per meter in our x direction. And again, that was a relatively simple one because we could just use this E equals V over D. However, if we had spatial dependence on our initial voltage, so if we had some spatial dependence here, again, we could go back to some of our equations in the previous unit and use those. Okay, so now we want to determine our polarization P. Okay, so using our equations, we know that our polarization P is equal to chi sub E times epsilon naught E, and we know that that chi sub E is the relative permittivity minus 1, then we have epsilon naught E still. So now we can plug in using our given relative dielectric, or our relative permittivity, which is also our dielectric constant, epsilon r. So for polystyrene, that's 2.55. And so remember, there's some common values or values of dielectric constant for common materials in your textbook. These are also things that you can find online relatively easily. Okay, so just plugging in then, we have 2.55 minus 1, which is of course 1.55. Our epsilon naught is 8.854 times 10 to the minus 12th, and that's farads per meter. And then we just found our electric field is 5 times 10 to the 5th volts per meter in our x direction. And so plugging all that in, we get that our polarization is equal to approximately 6.862 microcoulombs per square meter. So remember, our units for polarization is charge per area, and that's also going to be in our x direction. Okay, so there's our polarization. All right, so the next thing we want to find is this bound surface charge density, rho sub ps. And so I didn't specify a surface, so really we have some freedom in choosing what surface we're looking at. And so it turns out only 2 of the surfaces are going to have a non-zero bound surface charge density. So if we think of course, this is a 3D structure here, this parallel plate capacitor. The only ones that are going to have non-zero are, and so that's going to go behind for some reason, but basically our sort of surface of the dielectric on this right side and the surface of the dielectric on this left side. And so unfortunately that highlighter is going behind the shape for some reason, but of course this is going to be the surface sort of between that black metal plate and that blue dielectric. So it's the dielectric right next to the metal. And the reason for that is we can think about our equation. So our bound surface charge density, or again, sometimes we'll call this our polarization surface charge density, is equal to the polarization dot our U sub n. And so remember, this U sub n is our outward unit normal. So this is outward unit normal vector. And so if we come back up here, we can see that for these 2 highlighted regions, it's going to be, in this case, u of x, and in this case, negative u of x. Now we could also have other ones. We could have, and we don't necessarily know the orientation, but let's say maybe up here on this top surface we would have u of z. On this bottom surface we would have negative u of z, and then we have a u of y sort of coming out at us, and a u of y, a negative u of y sort of going back into the page. And so that's drawn kind of poorly, particularly for the u of y's. But of course for a cube we expect to have sort of 6 faces. Now for any of the other 4 for our z or y directions, we see that if we have u of z or u of y being dotted with our polarization, which is in the x direction, that's going to result in 0. So the only 2 places that we have non-zero bound surface charge density are on our x and negative x directions. So let's go ahead and focus on this one. So we can say, let's look at this surface here at our x equals 2 millimeters. And so all we have to do is just plug in, and so now we have our polarization dot u of x, and of course u of x dot u of x is just going to be 1. So we can then say that our bound surface charge density, or our polarization charge density, is approximately 6.862 microcoulombs per square meter. And so of course what we could see is if that was negative u of x, so if we had, so we can say rho p of s on that other side would just be p dot negative u of x, which is of course just negative 6.862 microcoulombs per square meter. And something we weren't asked about, but I want to talk about briefly, is our bound volume charge density. So how much bound volume charge density due to polarization do we have in the volume of our dielectric? And so we could do that from our basic equation. So we could say our bound volume charge density is equal to negative divergence of our polarization. And what we see is because our polarization here has no spatial dependence, when we plug into our divergence equation, we get that this is just going to be 0. And so as expected, because we've not added any charge to this dielectric, if we sum the total of our rho sub ps and our rho sub pv, we get that the net charge is 0 because initially our dielectric was neutral. So it remains neutral after this voltage is applied as well. So we see that this surface charge density sort of cancels out with this surface charge density here, and then we have 0 volume charge density. And as we explained, we have 0 surface charge density on the other 4 sides of the cube that don't have unit surface normal vectors in the x or negative x directions. If you want to get some more practice using these types of equations, you can look at the examples on page 192 to 195. So that would be useful for more practice. And as always, as you're working through those, if you have questions or issues, definitely let me know.